Now if we look at how wavelength affects things, again, if we're most interested in finding out what happens to any quantity, in this case the spreading angle, then a useful trick with a mathematical expression or an equation is to make the thing we're interested in this case the spreading angle, the subject, and then it becomes really clear what influences the subject. So in this case we're now looking at the wavelength, and it's really obvious to see if we have light with a long wavelength, in other words red light, then the spreading angle is going to be big. If we have light with a small wavelength, such as violet light, then the spreading angle is going to be small. This also explains the coloured fringes, which you see if you think back to those rave glasses which I bought you. The central fringe, m equals 0, as we know is white, because all the wavelengths meet there, and all colours constructively interfere with each other, and all colours together make white. Then we have the minima either side where there's no colour, and then we have the bright fringes. And because the red light spreads the most and violet light spreads the least, the innermost colours either side, because remember it's symmetrical, the innermost colours of these bright fringes are violet, and then it goes through to red on the outside. Then of course we have the minima again, so the no colours, and then we have another coloured fringe, but again in these other coloured fringes the violet is on the inside and the red is on the outside. Resolving. So resolving means how much of a given force or a speed is acting in a particular direction. So here's a really trivial example. If we have a box and we have 10 newtons force acting on it, how much of this force is acting horizontally? Well, 10 newtons. All of it is acting horizontally. Whereas if we think about how much of this force is acting vertically, well, none of it's acting vertically. Now this is quite a simple situation, and normally it's not quite as obvious as that. So here's an example. Imagine you've gone to B&Q and you've got a lot of heavy stuff and you put it in a trolley and you're dragging that trolley along. Now let's say for whatever weird reason you are pulling this trolley in the most stupid, inefficient way you can pull the trolley. So you've got an 80 newtons pull and you're pulling it almost vertically straight upwards at 70 degrees pull. And you know yourself, if you're doing this, then you might possibly lift this wheel off the floor, but you're certainly not going to be pulling it along in the direction you want to go in any way efficiently. Now why is that? Because hardly any of this force, hardly any of this 80 newtons force is acting along the way that you actually need to go. And you don't need a calculation to kind of get a sense of that. If you pull it almost vertically, then very little of that pulling force of 80 newtons is going to be acting along the way. But at higher, we have to be able to calculate exactly how much of that is acting in the desired direction, and in this case the desired direction is along the way. So we've got 80 newtons going that way at an angle of 70 degrees. Now I've spoken about this nifty trick before. If you've got a vector going in one direction and you want to say, well, how much of that is acting in a given direction? If your given direction, you reach that given direction by rotating through or crossing a known angle, so in this case 70 degrees, we start up there and we want to rotate around to get to horizontal. If you're crossing a known angle, then it's the number cosine 70. So crossing a known angle, it's cosine. If it were to be the vertical one, then it would be 80 sine of the angle, in which case it would be 80 sine 70. In this case we're crossing the known angle to get to the horizontal, so it's 80 cos 70. Never leave your answer in physics like that. I don't know if you do in maths, but you never leave it in physics, always work it out, and that comes to 27, which kind of makes sense. So a really small proportion of this 80 newtons is acting horizontally. Now another way of doing this, if you want to, I suppose this is the more rigorous way, although that way will always give you the right answer. A more rigorous way is to find a right angle triangle. So here the hypotenuse is 80, you want the adjacent. So if we've got the adjacent and the hypotenuse, we know we're going to use cosine. So cosine of 70 is the adjacent over the hypotenuse. And rearrange to find the adjacent and you end up with the same number. Here's another example. So we've got two drones and they're carrying an Amazon package, and they've got string there, or cord, and the angle between the string and the vertical is 35 degrees in each. The mass is 3.4 and we've got weight force acting down the way and tension in each of the cables. So the drones and the attached package are hovering. Calculate the tension in each cable. Well, if they're hovering, then Newton's first law says that the sum of the forces going up must equal the sum of the forces going down. So forces are balanced. So how much of each of these are in the are in the vertical direction? Well, we take our tension and we're crossing the known angle. So it's going to be T cos 35. But we've got this T cos 35 and we've got this T cos 35. So T cos 35 plus T cos 35 is the weight force, which is W equals mg. So this is 2T cos 35 is 3.4 times 9.8, because that's mass times g. And then you solve it and you find the tension in each cable. Okay. If you want to add more lines of maths working, that's totally fine. But I'm just trying to show you the principle of doing the resolving. Here we have a gymnast. I don't know if you've seen the gymnastic discipline called it's the rings, I think. So this person, the rings are, as the name suggests, rings on the ends of ropes, and this, you kind of suspend yourself above the ground, so this person's feet won't be on the ground, they'll be kind of suspended. And to begin with, this person is kind of vertical, the arms are down, so they're holding on, and the cables are vertical. So if this person has a mass of 50 kilograms, we can work out what tension is in each of these cables or strings or cords or ropes, whatever they are. So we've got T there and T there, which is 2T equals the weight force going down, which is mg. So again, solve it however you want to solve it, but we know the tension in each cable therefore is 245 newtons. So gymnasts are usually ridiculously strong, so let's say this person now pushes these cords, these cables, these ropes outwards at an angle of 10 degrees. And you kind of intuitively know, if you imagine that you're there, imagine you're the gymnast, that you now know there's an awful lot more force, there's an awful lot more tension in your arms that you have to provide. And so this is because there's an awful lot more tension in these ropes, and we can work this out. So there's the tension force, and we want to think about vertical, because the force is up the way, the net force is up the way, the total force up the way must equal the weight force down the way, because this person is stationary. So if there's T, and we want to turn through an angle to get to the vertical. Now, this sometimes is the case. Don't know if you've heard of the Z angles, hopefully you have, but if we know that this angle is 10 degrees, can you see this? If we were to do that, that would form kind of a Z shape. That's meant to be horizontal, the vertical going up, and so this would also be 10 degrees, and similarly this would also be 10 degrees. So we're crossing a known angle of 10 degrees, crossing a known angle of 10 degrees, so we have two lots of T cos 10 equals the weight force going down. Again, solve to find that, so 249. So the tension in the ropes in this case has gone up. Because now only a proportion of the tension force is acting vertically, the overall tension force now needs to be greater to provide this. I suppose it's a bit like if you normally, do you kids still get pocket money? I don't know. So let's say you get a certain amount of money every week, pocket money, and you spend all of that money each week buying sweets. But then let's say you've got your granny's birthday coming up, so you need to buy granny a birthday present. But you still want to buy £10 worth of sweets, or however much you normally spend on sweets a week. So if you want to still buy £10 worth of sweets, plus also have the money to buy granny a present, then you're going to have to get more money overall, aren't you? Maybe you're going to have to do a bit of work for somebody or whatever to get more money overall. So yeah, I don't know, maybe that analogy helps, maybe it doesn't. But in this case, if less of the proportion of if the proportion of the force acting vertically is less, if these are no longer vertical, then in order for that amount of force needed to balance out the mass to exist, then the overall tension must be greater, and that's what we've found. Now we're on to uncertainties. So a person runs 100 meters. They do this for 5 consecutive days, and these are the times they get. Now notice, even though it's the same person, these times are very slightly different, even though it's the same runner running the same distance. Now why would they be different? And you can see that they probably would be different. Well, maybe it's windy on some of these days, maybe the person's tired, maybe they have a stitch one of these days, so they don't do very well, maybe they miss breakfast on one of these days. Okay, so these are called random uncertainties. Random uncertainties can be often hard to predict, but what it means is you can get, often hard to predict, but what it means is that the same reading repeated actually gives you different numbers. Even though theoretically, because it's the same thing happening in the same way, theoretically they should be the same. But because of these random effects, the same measurements in exactly the same way gives you different outcomes. Now, as it says here, you can guess a number to represent the size of the random uncertainties affecting your reading. So here are the readings. I've just written them out again for convenience. The way we find a number to represent the size of these random uncertainties is we take the biggest reading and then subtract the smallest reading and divide it by the number of readings. So the biggest reading here is 15.2, the smallest number is 13.8, so do 15.2 minus 13.8 divided by the number of readings, 1, 2, 3, 4, 5, divided by 5, and that comes out to be plus or minus 0.3 seconds. A runner with a smaller random uncertainty, what does that mean? Well, a runner with a smaller random uncertainty would be a more consistent runner, because these random distraction events, these random distractions, cause less variation in their performance. So a smaller random uncertainty means the kind of fluctuations are less. So I suppose a coach would prefer a runner with smaller random uncertainties. Now, staying with the running theme, imagine there's a running camp and you've got a bunch of pretty keen runners and they all run 100 meters, and let's say that you've got a stopwatch which works to 1 decimal place. So they all get 13.8 seconds. Now, do you think they're going to be happy bunnies? Well, no, they're not. Because if they all get 13.8 seconds, then what this actually means is, if you think about kind of the range, it could be from anything from 13.5 seconds all the way up to 13.85 seconds. Well, I suppose when you get to a 5, then there's some maths conventions, in some mathematical conventions, which say you round up to the next one. But really, between 13.75 and 13.85, it could be anything between there. And so if these people wanted to find out who really was the fastest, you'd need a stopwatch which goes to another decimal place. So this says a stopwatch with a 1 decimal place reading has not enough precision here, as there is a large scale reading uncertainty. So scale reading uncertainties are about the kind of the preciseness, the accuracy, the fineness of detail in your measuring device. So scale reading uncertainties, how do we get a number which represents the size of the scale reading uncertainties? Well, if it's a digital device, meaning a number is displayed and that number kind of changes, then we say the scale reading uncertainties in that digital device is plus or minus 1 in the farthest right digit. So that's a very clunky expression, but if you've got, we'll take this 13.8, the farthest right digit is this 8 figure, so the scale reading uncertainty is plus or minus 1 of this farthest right figure. So it's plus or minus 0.1 seconds. It's always 1. Analog, that means there's like a dial which actually physically moves. The scale reading uncertainty is plus or minus half of the smallest marked on increment. So for an example, think about the rulers which we use in science. They're typically marked on millimeters, aren't they? And so if you're going to measure something with the science rulers, then the scale reading uncertainties in the science rulers are plus or minus half of 1 millimeter, or plus or minus 0.5 millimeters. And it's maybe worth saying that for other contexts,